Welcome to the Wearable Sensing DSI Signal Quality tutorial, where we will go over how to ensure clean, artifact-free recordings. For information on how to set up the headset, watch your respective system's DSI donning tutorial. Once you have donned the headset and turn it on, connect your headset to DSI Streamer via Bluetooth or wired mode. For more information on setting up the various types of connections, see the Connecting Headset to PC video tutorial. Choose the source as either headset for live EEG or file to watch pre-recorded EEG. Next, choose the headset type. When viewing pre-recorded EEG, click play to load the .dsi file. Note that all the functionality of DSI Streamer is the same on a replayed file as it acts as if it was live, except you can speed up and slow down the recording. To connect the headset for live EEG, go to Source, select Headset, choose the headset type, ensure the correct COM port, and click Connect. Once connected, press play. After connecting the headset, the next step is to check signal quality. To begin this process, navigate to the Diagnostic tab. Turn the impedance driver on to monitor impedance. There are 3 columns associated with each sensor on the headset that will determine whether the color of the sensor above is green, yellow, or red. The first column under Z is impedance. Impedance is the measure of how good the contact between the skin and the sensor is. Target values should be below 1 megaohm, but not less than 0.1 megaohm. The next column under N is noise. Noise is the measure of the root mean square, or RMS, of the amplitude of the EEG signal over the past second. Target values should be less than 20 microvolts when the subject is sitting still, not blinking, with their eyes fixated on a spot. The last column under BL is baseline level. Baseline level is a measure of the DC shift of the electrodes and relates to how well equilibrated the silver-silver chloride is on the skin. As your skin breathes naturally, the chloride ions in sweat exchange with the chloride ions on the electrode tips, creating a microenvironment that over time will reach an equilibrium. As this occurs, the baseline level settles closer to zero. Target values are less than plus or minus 5,000 microvolts. All 3 of these columns must be below their target value for the sensor location to show green. If any one of these values is above their target value, the sensor location will show yellow. If the impedance is above 10 megaohm, the sensor location will show red. If the impedance is between 1 and 2 megaohms, simply take the tool and press the sensor down on the scalp for 1 to 2 seconds without rotating the sensor, and then click Reset. The reset button temporarily shorts the inputs of the amplifier, which allows the signal to settle back quickly. If the impedance is above 2 megaohms, take the tool and rework the sensor through the hair by rotating left and right and then pressing the sensor down for 1 to 2 seconds, then click Reset. If the baseline level is above 5,000 and not gradually decreasing, take the tool and press the sensor down on the scalp for 1 to 2 seconds without rotating the sensor, then click Reset. Once you have confirmed that all 3 columns are underneath the target values for each sensor, you can exit out of the Diagnostic tab and begin a series of visual assessments on the quality of the signal. Begin with an eyes open test, where the subject must keep their eyes open without looking around. In this instance, the subject was moving their eyes, causing EOG artifacts, which we will go over later in the video. What we're looking for is to make sure there isn't any significant noise and that we're gathering clean EEG signals. This is an example of what clean eyes open EEG should look like, with the exception of some minor eye movement. Next, conduct an eye blinking test, where the subject must blink rapidly. What we're looking for are blink artifacts on the frontal channels, ensuring we are picking up these low-frequency signals. Next, conduct a jaw clench test, where the subject must clench their teeth together. What we're looking for are EMG artifacts, ensuring we are picking up these high-frequency signals, that they are showing up on all channels, and that the signal can recover after the artifact. Next, conduct an eyes closed test, where the subject must relax with their eyes closed. What we're looking for is alpha activity on the posterior channels. Keep in mind the size and prevalence of alpha activity can range from subject to subject. It is not uncommon for subjects to produce very little alpha activity. However, it is still recommended to check alpha activity generation. Next, we want to ensure our signal is not being compromised by electrical or motion artifacts. To do this, open up the Montage tab at the top of the screen, unclick Headset Default Montage, add an additional plot to the screen, then go to the right-hand side of the screen, scroll down till you see the extra plot labeled X1, click the plot, and then change the first reference to CM, otherwise known as the common mode. You can also change the color to make it easier to differentiate between the common mode and EEG. The common mode channel is a visual representation of all the electrical signal that is common on the body. What this means is when someone walks, taps their foot, or rubs their feet on the carpet, they are generating electrical activity that can be picked up by the electrodes. The common mode is not filtering any data or doing artifact rejection. The mechanical design of the system allows us to be immune to electrical and motion artifacts. To test the effectiveness of the shielding on the electrodes, have the subject either tap their foot on the ground or have someone stand behind the subject tapping their foot with their hands next to the headset. What we're looking for is pickup of this electrical activity on the common mode channel, but no change in the EEG signal at all. To demonstrate the immunity of electrical artifacts, turn off the low-pass filter. At this point, you will see a high frequency that shows up on all the channels. This is because we did not turn off the impedance driver, which sends signal at 110 and 130 Hz. Turn off the impedance driver and the EEG signal will go back to normal. Now that the low-pass filter is off, as well as the impedance driver, to demonstrate the immunity to electrical artifacts, grab an AC power cord, in which we're artificially injecting 60 Hz mains frequency onto our body. You will see the signal drastically on the common mode channel, but the actual EEG is unaffected. To test the effectiveness of the electrical and mechanical shielding on the electrodes, have the subject walk back and forth. Make sure when the subject is walking to have them focus their eyes on one point to avoid picking up EOG artifacts. What we're looking for is the pickup of this electrical activity on the common mode channel, but no change in the EEG signal at all. It is important to note that you can conduct these tests without the common mode channel. What we're doing is making sure no electrical or motion artifacts are showing up in the EEG. The common mode is just helpful to visualize the artifacts that the system is protecting the EEG signal from. The common mode channel is not digitized and therefore not available for visualization in some DSI systems. To remove the common mode channel, either decrease the plots on the screen back to 21 or select Headset Default Montage. Now that the signal quality metrics are in their target range, we need to visually inspect the signals to ensure they are artifact-free. In the next section, we will look over the types of artifacts there are and how to deal with them. The first artifacts we will address are EOG artifacts, when the subject is moving their eyes around. This is an example of what the signal looks like when the subject moves their eyes left to right. This is an example of what the signal looks like when the subject moves their eyes up and down. In order to avoid these artifacts, make sure the subject does their best to focus their eyes on one spot when possible in your experiment. Alternatively, there are many EOG artifact removal tools available in third-party EEG analysis software. Another source of artifacts are EMG artifacts, which is when there is unnatural muscle tension that occurs in different areas of the body. In this instance, the subject is exerting unnatural muscle tension within their jaw. You can see the noise is very pronounced and shows up in all channels. However, some subjects can generate EMG artifacts only on T3 and T4 channels. To combat these jaw EMG artifacts, have the subject open their mouth and yawn, attempting to loosen any muscle tension going on in the jaw area. Another source of EMG artifacts can be from bad posture, such as when the subject is slouching with their neck forward. You can see increased noise show up on the O1 and O2 channels when there are neck EMG artifacts occurring. To combat these artifacts, have the subject sit up and have good posture. This means the head is sitting square above the shoulders and the shoulders are relaxed. Jaw and facial muscles are relaxed, no tension in the brow, nor smiling. The last potential EMG artifact we will go over are EMG artifacts that can occur on the forehead. This happens when the front band is either too tight or unnaturally pulling the skin on the forehead up, causing increased noise on channels FP1 and FP2. To combat these artifacts, release tension on the forehead by pulling the skin down or lift and reposition the front band. The next artifact that can occur are motion artifacts. Motion artifacts are when the signal is being compromised as a result of the electrode not sitting sturdy on the head. As you can see, when the subject is walking, you can see consistent spikes on some of the channels at each footstep, suggesting those electrodes are bouncing around when the subject is moving. To combat motion artifacts, make sure the headset is tightened along the front band and the top crown. In this instance, the top crown was very loose, so it's important to tighten the elastic so that the top crown is no longer bouncing up and down. As you can see, once the headset is tightened properly and the electrodes are making good contact, motion artifacts do not occur when the subject is walking. It is important to note that it's only necessary to tighten the headset to this level if you want to ensure resistance to motion artifacts. If your subject is not planning on walking around or moving aggressively, tighten the headset just enough so the subject is still comfortable. The next artifact to look out for are sweat artifacts. Sweat artifacts will begin with small pop spikes, such as the ones highlighted, and will gradually get worse over time if the source of the sweat is not addressed. Sources of sweat include external temperature, such as being in a hot room, internal temperature, such as working out before recording, emotional temperature spikes, such as if a person is stressed, medical conditions, and spicy foods. As you can see, if the source of sweat is not immediately addressed, sweat artifacts can become extremely significant. If the sweat artifacts reach extreme levels, such as what is shown, you must address the source of sweat. In the case of external temperature, such as a hot room, make sure the AC is on and have a fan blowing directly on the subject. Make sure the fan is behind the subject and not in front to avoid increased eye blinking artifacts. In the case of internal temperature, make sure the subject does not work out or do any vigorous activity prior to donning the headset. In the case of emotional temperature spikes, do your best to calm the subject down and create a relaxed and stress-free environment. In the case of medical conditions, make sure to take note of these before recording or avoid experiments on subjects with such conditions. In the case of spicy foods, avoid eating spicy foods prior to recording. Even though sweat artifacts can drastically distort the signal, they can be combated with relative ease. It is important to address the sources of sweat before recording to avoid any unwanted artifacts. In this specific instance, the source of sweat was due to external temperature. So to address the source of sweat, the subject is first going to take away the space heater that is directly in front of his face. Then, the subject is going to put a fan on. And as you can see, the sweat artifacts begin to settle very efficiently. Sometimes it may take longer. However, we can see a different kind of artifact now arising on channels F7. Notice the irregularity in this artifact? This is called cardioballistic artifact, otherwise known as CBA, and it can be sometimes small, as in this case, and might be easily missed between EOG artifacts, or it may be pronounced as in the next example. Cardioballistic artifacts, otherwise known as CBA, is when a blood vessel begins to pulse under the electrode and can be seen as a downsloping ramp on any given channel with the consistency similar to a heartbeat. There are three methods to combat against CBA. The first method is to slightly shift the electrode 1 millimeter in either direction in an attempt to move the electrode off the blood vessel. Once you move the electrode, click reset and see if the CBA has gone away. If the CBA does not go away after shifting the electrode 1 millimeter in one direction, the next step is to shift the electrode 1 millimeter in the other direction. Then click reset. In this instance, you can see the CBA has not settled, so we move on to our second line of attack against the CBA, which is to take the tool and turn the sensor either left or right. All we want to do is shift the position of the electrode tip in another attempt to move the electrode off the blood vessel. Once you shift the electrode, click reset and see if the CBA has gone away. In this instance, we were able to defuse the CBA, but if the first two methods to combat the CBA are unsuccessful, the last measure is to take 70% isopropyl alcohol and use a Q-tip to rub the skin where the CBA exists. This will cool down the skin and help induce the local vasoconstriction, which pulls the blood vessels away from the surface of the scalp. Furthermore, this slightly abrades the skin's outer layer, which contributes to the CBA artifact. Now that we have passed our signal quality check, we are ready to record. How to record will be covered in the DSI Streamer tutorial. Please refer to the next video for an in-depth tutorial on DSI Streamer. Thank you for your interest in wearable sensing technology.